In this video, we're going to talk about functions. So there's lots. We've probably used these words before. A lot of the equations we've worked with are functions. Some of them are not, however. But we're going to start off a little bit more generally and talk about relations. Okay, so a relation from a set X to a set Y is a correspondence between set X and set Y. Okay, so any correspondence. So it could normally, a common way to write it is as a set of ordered pairs. Okay, so ordered pairs are like the points with the coordinates x, y. Okay, where little x is in X and little y is in capital Y. So you take one element from set X and you pair it with one element from set Y. Okay, that's what we call a relation. So some examples of relations, maybe you go from the set of people to a set of numbers, and you might correspond them by their age. Okay, so there's an example here. This is another instructor at Camosun. I think this is a bit old, but probably at the time he was 31. So we would take him and his age and pair them together. So it's an element from the people set and an element from the number set paired together because this person is that age. Another example would be maybe if you take from the set of cartoon characters and you maybe pair them with other cartoon characters or even themselves. Maybe we use the relation that one of them is a sibling of the other. Okay, so that means if you think of the ducks, okay, Huey and Dewey are siblings. Huey and Louie are siblings. Louie and Huey are siblings. All of these would be in the relation because they satisfy the correspondence. Okay, so there's 4 common ways to express relations between two sets. Okay, one of them is using a picture, so we call it a mapping. Okay, so you have some set X, and you're going to some other set Y, which maybe could be the same set. Okay, and then you have points in here, okay, going to points over here. Okay, so maybe you have, I don't know, A, B, C, and then like 1 and 2. Maybe A goes to 1, B also goes to 1 for some reason, maybe C goes to 2. Okay, so you can individually write or draw, I guess, where each element in your X set, what it's paired with in your Y set. Okay, you could also write this as a list of ordered pairs. So maybe if I'm talking about the relationship R, if I do this one above, I would have A paired with the number 1, B would also be paired with the number 1, and C would be paired with the number 2. So I could write that relationship out as a set of ordered pairs. Okay, now I can't really make an equation for this, but you could use an equation. Okay, so like for instance, one that we've seen would be an equation like this. So the ordered pairs, the list of ordered pairs is all of the points that satisfy this equation. So remember that they look like ordered pairs as well. And then you could also exhibit this with a graph. Okay, so if I just graph that one there, it's the unit circle centered at the origin. Okay, so it's a circle with radius 1 centered at the origin. Okay, so there's the center. And then we have the points 1, 0, 0, -1, -1, 0, and 0, 1. Okay, so that corresponds to the equation up above. That's another way to talk about that relation. Okay, so more specifically, a function from a set X to a set Y is a relation. Okay, so it's a special type of relation that associates each each element of the X set to exactly one element of the Y set. Okay, so you don't want to have multiple options for your X's. So you have to take everything in your X set has to be mapped somewhere, but it only goes to exactly one place. Okay, so we say little x in X corresponds or maps to little y in Y if X is associated with Y. And so we write that with an arrow, or in the picture you would write like X goes to Y. So we often talk about functions. We name the function. Okay, so often we name f or g or h. Those are common, but any letter is fine, really. And then if x is related to y, we often write f of x equals y. Okay, so the way that you read this is f of x is y. Okay, so that says that f sends x to y. Okay, so if we had the little picture of the mapping, okay, we'd have our X set and our Y set. There would be little x in here, little y in here, and the function f would take x to y. Okay, so for example, if we had a function from the integers, x is the integers, to y, which is the non-negative integers, now we've given the function as an equation, so f of x equals x squared, then f of 2 would be 2 squared, which is 4, and that's why 2 would go to 4. Okay, similarly, negative 2 would also go to 4. Okay, and f is the name for this function. So, how do we tell if things are functions of a function of one or the other? So let's say we have this equation, okay, x squared is equal to, x squared plus 4y equals 1. We want to know, is y a function of x? And is x a function of y? Okay, so let's check this. Okay, so let's say y a function of x. We're going to check that first. So that means I want to solve for y. Okay, and see if I plug in an x value, do I only get one y value? Okay, it's easier to tell if we solve for y. So we're going to have 4y is equal 1 minus x squared. So that means that y is 1 minus x squared over 4. Okay, now from here, think about plugging in an x value. Do you have any options? So if I plug in x equals 1, I'm going to get 1 minus 1 squared. So 1 minus 1 on the top is 0. And 4 divided by 4, that's going to be 0 as well. No matter what number I plug in, I get exactly one y value. Okay, so here, y is a function of x. Okay, since each x value gives exactly one y value. Okay, now let's say, okay, is x a function of y? So now I want to know, if I plug in a y value, do I only get one x value? Okay, so here again, this time we're going to solve for x. Okay, so x squared is 1 minus 4y. So if I take the square root of both sides, I have to add a plus or minus, but I get the square root of 1 minus 4y. Okay, now here we can see that x is not a function of y. And we can see that since one y value can result in multiple x values. Okay, so for example, if I take y equals 0, for instance, then x is equal to plus or minus the square root of 1 minus 4 times 0, which is going to be plus or minus 1. So I get both. So 0 is mapped to 1, and 0 is mapped to negative 1. Okay, so because 0 goes two different places, then we have it's not a function. Okay, so that's the idea. So given a function f from x to into y, the domain is the set of all inputs. Okay, so that's going to be the things you put in. So that's going to be your x set. The codomain is all possible outputs. Okay, so that is actually your y set, because it's everything that you could match things in x with. And the range is actually the set of actual outputs. Okay, so what I mean by that is it's all y values in the y set such that f of x is equal to that y value for some y. Okay, so let me just draw a little picture here. Okay, so if this is your x set, and over here is your y set, okay, so maybe our function f takes this one to this one, this one to this one, maybe this one also goes to that one. Okay, so this x is the domain. Everything in x goes somewhere. Y is the codomain. Okay, but only these two elements are going to be in the range, because they're the ones that get mapped to. The other two do not. Okay, so they're only in the codomain, not in the range. So let's do some examples here. So determine if the following relation is a function. Okay, and if it is, we're going to state its domain and range. So you could do, it's useful actually to think of these as pictures. Okay, so I have an x set and a y set. Okay, so here, my x set, I want to put all the x coordinates. Okay, so that's going to be 0, 4, 2, and negative 1. Okay, so I'm going to have 4 dots in here. 0, 4, 2, and negative 1. Okay, and then 0 goes to 3, so I have a 3 over here. Okay, so 0 maps to 3. 4 maps to 1, so that's a new point over here. 2 maps to negative 1, so that's a point over here. And negative 1 also goes to 3. Okay, so it goes over there. So everything in the domain goes exactly one place in the codomain. Okay, so yes, this is a function. Okay, and the domain is going to be all of the x, so it's the set 0, 4, 2, and negative 1, all the elements that were in x. And the range is everything we map to, so that's going to be 3, 1, and negative 1. Okay, let's try another one. So here, again, I think we have the same x. Oh, there's no negative 1 anymore in x. Okay, but everything else is the same. So my x, I have a 0, a 4, oops, and a 2. And over here, I have the 3, the 1, the negative 1. Okay, so I get 0 goes to 3, 4 goes to 1, okay, 2 goes to negative 1, and then 4 goes to 3. Okay, so notice that 4, I have an arrow that goes to 3, and also an arrow that goes to 1. So that means that f of 4 is equal to 3, and f of 4 is equal to 1. Okay, so 4 gets mapped two different places, so this is not a function. So the elements in x can go exactly one place in y. Okay, so this 4, which is in our x set, is sent to 2 different places. Okay, so that's a bad thing. Okay, I'm going to leave this one for you to do. Let's move on. So, f is a function, okay? It's the name of the function. F of x is a value, okay? It's actually the y value. It's the place where the x is sent. Okay, so another actually picture for the function, which is also useful to think of, is it's like a machine. Okay, so this is your function machine. So what we do is we put in an x value, okay, and it spits out an f of x value, which is a y value. Okay, so that's sort of how you can think about it. So f is doing something, so you put in x, inside the function here, something happens, you hear some clicking, and then it spits out a new number, which is your f of x value. Okay, so that's the idea. So we say y equals f of x, then x is called the independent variable. Okay, because that's the one that we're assigning somewhere. So we get to pick that one, essentially. And then y is the dependent variable because it is what results given what we picked. Okay, so that's how we refer to those things. Okay, so using this notation is very important, okay, and it's going to be going forward. So we want to practice it. So I'm going to do a few of these. So let's say that our function, f of x, so this is the name of the function. So if we input x, this is what it outputs. Okay, so the thing that's inside the bracket, this is our input, and this is the output given the input. Okay, so that's what it looks like. Okay, so computing f of 3 is probably you know how to do. So everywhere you see x, we're going to put in 3. Okay, so 3, this is our input. Okay, so that's what we're putting into our machine, and then we're using this formula to get our spit out value. Okay, so it's going to be 3 squared minus 3 times 3 plus 2. So I'm going to get 9 minus 9 plus 2, so I get 2. Okay, so f of 3 is actually equal to 2. Okay, now if I do f of x plus f of 3, just do the f separately, okay, because the plus, so the brackets here, this, I'm inputting two different things. Okay, so x is an input, 3 is an input, okay, and then I'm adding the results together after. Okay, so that's going to be my output for f of x, f of x is x squared minus 3x plus 2. And my output for f of 3 was 2. Okay, so this part here is f of x. And then I want to add to it f of 3. So then I can just simplify this. So it's going to be x squared minus 3x plus 4. Okay, so that would be f of x plus f of 3. Okay, now this next one looks very similar. Okay, but notice that it's only one f and the brackets are on the entire x plus 3. So what that means is that this whole thing is my input. Okay, so how I do that, when I'm using the equation, everywhere I see an x, which is those two spots, I'm going to put in x plus 3. So I need to replace the x with my input, just like we did for 3. Okay, every time we saw x, okay, in our formula, we replaced it with a 3. So we're going to do the same thing here. So it's going to be x squared, so that means it's x plus 3 squared minus 3 times x plus 3 plus 2. Okay, so that was my x. Everywhere I saw an x, So you could think about the x as like a box. Okay, so what you actually have, oops, for your formula, so x is kind of like a placeholder. Okay, so you have f of something. Okay, it could be anything, could be a smiley face. Okay, is the something squared minus 3 times the something plus 2. Okay, so each time we change what's in our brackets of f, we're changing what goes in the something. Okay, so maybe it's like a happy face. Okay, then I would just put it into each of the boxes. Okay, so that's what we're doing. That's what we did down here. And now we just want to simplify. Okay, so x plus 3 all squared is x squared plus 6x plus 9. And then I need to expand the negative 3 through. So I have minus 3x minus 9 plus 2. And I end up getting x squared plus 3x plus 2 as my f of x plus 3. Okay, now I'm going to leave these last ones for you to try, but I'll fill them in a subsequent video. This one is probably the hardest, so maybe do that one last. But it is one that we're going to need very soon, in fact, right away. Okay, so we are going to do one like that. So the difference quotient is a very important thing in calculus. So we're going to practice it in pre-calculus. So it's the expression f of x plus h minus f of x all over h. Okay, given that h is not 0. Okay, so that's the difference quotient. You want to remember what that is. Okay, so keep this in your mind. Difference quotient is this thing here. Okay, so let's do an example. We'll do the first one here. So find and simplify the difference quotient for this f of x, so 2 over x. Okay, so we take f of x plus h minus f of x all over h. Okay, now it might be useful, I don't know, okay, to think about what these things are. So what is f of x plus h? F of x we already know, it is 2 over x. But f of x plus h, remember, okay, x plus h is my input. So everywhere I see x, I'm going to put in x plus h. So this is going to be 2 over x plus h. Okay, so that means that what I have over here is 2 over x plus h minus 2 over x all over h. Okay, so then I just want to simplify this. There's obviously different ways to simplify. We've done things like this before. Okay, this is a complex fraction, so you can kill off the denominator, or you can make a common denominator and simplify the top. Okay, that's what I like to do. So I'm going to multiply this term by x over x, and this term by x plus h over x plus h to make a common denominator there. So it's going to be 2x over x times x plus h minus 2x plus h over x plus h all over h. Okay, so then I can put those together. So it's 2x minus 2x plus h over x plus h. And this is my big line. Okay, so I don't want to forget that's where my fraction line was. So now if I simplify the top, you have to expand this in. So I get 2x minus 2h over x plus h all over h. So 2x's cancel because one's plus and one's minus. So I have minus 2h over x plus h all over h. And h is, I could think of it, so I want to think of it as a fraction. Okay, so that I have a fraction over a fraction. So then I'm going to flip the bottom one and multiply. So I'm going to multiply by 1 over h instead of dividing by h over 1. And now because these are all multiplying, the h's cancel out. So I end up getting negative 2 over x times x plus h. Okay, now you won't understand why this is a good place to stop, but this h on the bottom is going to be a problem when in calculus. So once you've canceled it, that's when you know you can stop. Okay, that's when you know you've simplified enough. Okay, so this is our simplified version here. Okay, now maybe I'll just make a note here. So instead of making a common denominator, on top, you could have multiplied top and bottom by the common denominator. Okay, and then you would have killed off the denominators fully. Okay, so it just depends what method you like better. I believe when we just did this in class that the students normally prefer the common denominator this term, but it varies. Okay, so if you prefer to kill off the denominators, that is fine as well. Okay, so I'm leaving this example for you. It's a little bit easier than the one we just did. So you want to find and simplify the difference quotient. Now, in all cases, the h in the denominator will always cancel. Okay, so if you simplify correctly, that h should cancel out with the on the top. So that's where you know you want to stop. And then you want to be careful how you cancel. Okay, hopefully we're getting more comfortable with that. So what this is saying is that you cannot cancel things like, this isn't like a difference quotient, but okay, so here I cannot cancel those. So this would be not equal to 2 minus 1 over 1 because it's not multiplied. So this one term doesn't have the x minus 1. It has to be multiplied, everything on the top and everything on the bottom, before you can cancel. Okay, that's why I was able to cancel here, because h is timesing everything, and here h is timesing everything on the top. Okay, so that's when you know you can cancel. Okay, so for a function given by an equation, sometimes they don't give you the domain. So if they don't tell you specifically what the domain is, you should assume that it's the largest set of real numbers for which the function's defined. Okay, so common things that are not defined that we often run into. Okay, divide by 0. Okay, so you want to watch for those. And negative values under even roots. Okay, so square roots, fourth roots, etc., etc. So I'm just going to do one of these. So if I had the function f of x is the square root of 1 minus x. Okay, so they haven't told me the domain. I need to find it. So what you want to think of is, what x values could I not plug in? Okay, the domain is a set of all x values that I can plug in, but it's normally easier to think, what can I not plug in? So what we need is for this thing inside the square root to be positive. Okay, so we need 1 minus x to be at least 0 in order for the square root to be defined. So if I add x to both sides, that gives me that 1 is bigger than or equal to x. Okay, so that means that the domain in interval notation here is going to go, so 1 is the biggest it can be, but I can be anything smaller. So it's going to go from negative infinity to 1, and I want to include 1 because if x is 1, then I have 1 minus 1 here is 0, and the square root of 0 is 0, so that's fine. Okay, so that would be the domain for that one. Okay, so you can also combine functions. So some ways that you can combine is by adding them, subtracting them, multiplying them, dividing them. Okay, so here's an example of doing all of those things. So here I have two functions. Okay, f of x is x squared minus 1. G of x is x plus 1. So if I want to add those functions, so f plus g of x is actually f of x plus g of x. So f of x we know is x squared minus 1. And then I want to add g of x, which is x plus 1. So if I just combine those, I'm going to have x squared plus x, and the 1's are going to go away. So I just actually have x squared plus x. That would be the sum of those two functions. Okay, if I want to subtract them, x squared minus 1 minus x plus 1. Okay, these brackets are important. The minus has to go to both things in g of x. Okay, so this is actually x squared minus 1 minus x minus 1. So I get x squared minus x minus 2 here. Okay, if I want to multiply them, so f of x times g of x looks like that. And then you could just expand it out. Okay, so I have to use FOIL. Okay, so it's going to be x, oops, I'm still in pink. It's going to be x cubed plus x squared minus x minus 1 when I FOIL that out. Okay, the division, so f of x is on the top here, divided by g of x. So that's what it looks like. Here we could actually simplify it. So it's going to be x, I can factor the top as x minus 1, x plus 1 over x plus 1, and now I can cancel those. So it's just equal to x minus 1. Now this is assuming as long as the bottom is not 0. So we can't cancel when it's 0 over 0. Okay, so that's the same thing as saying x is not equal to negative 1. Okay, so this function, the quotient of them is equal to this function everywhere except at negative 1. So that you're going to end up with a hole in the graph there. Okay, so that's what it would look like. So the domain's going to be different, but otherwise the functions are equivalent. So now that I've talked about domain, here we go. If you add, subtract, or multiply two functions, the domain is going to be all x values in the domains of both f and g. Okay, so as long as you could plug x into both f and g, you can plug x into f plus g, f minus g, and f times g. For the quotient, you have this one extra condition. Okay, so it's all x's in both domains, except ones where g of x is equal to 0. Okay, so because we're dividing, we need to be careful that we don't divide by 0. Okay, so we want to get rid of, so these would be fine normally for g of x, but because g is on the denominator, now we need to throw away those values as well. Okay, and then I'm going to leave this one for you. Okay, so you want to compute f plus g, f minus g, f times g, and f divided by g with these two functions, and think about what the domains would look like. Okay, so that is intro to functions, and especially function notation. Okay, that's going to be very important.